Distributed Fiber Optic Raman Temperature Measurement DTS system is based on the Optical Time Domain Reflection (OTDR) principle of optical fibers and the Raman scattering effect of optical fibers. The laser pulse interacts with the fiber molecules and a variety of scattering occurs, such as Rayleigh scattering, Brillouin scattering, and Raman scattering. Raman scattering is due to the thermal vibration of the fiber optic molecules, which produces a Stokes light that is longer than the wavelength of the light source and an anti-Stokes light that is shorter than the wavelength of the light source. The fiber is modulated by the external temperature, causing the anti-Stokes light intensity in the fiber to change. Anti-Stokes to Stokes ratio provides an absolute indication of temperature. The use of this principle to achieve the distributed measurement of the temperature field along the optical fiber, combined with high-quality pulsed light source and high-speed signal acquisition and processing technology, we can get the accurate temperature value of all points along the fiber. According to the above principle, we look at the specific realization of the system. First of all, the DTS system needs a pulsed laser. The output light is 1550 nanometers. The typical pulse width is 10 nanoseconds. The peak power, 1030 W. The trigger mode is external trigger, and the pigtail type is a multi-mode fiber of 62.5/125. The output port of the pulsed laser is connected to the 1550 port of the 1x3 Raman WDM module. Then the temperature measurement fiber optic cable is connected to the COM port of the WDM, and the remaining 1450 and 1660 ports are connected to the two input ports of the dual-channel APD respectively. The dual-channel APD photoelectric converter converts the anti-Stokes and Stokes light into electrical signals. The electrical signals are output through the SMA interface and connected to the two acquisition channels of the acquisition card with RF cables. The capture card has an integrated signal trigger function. Connect the trigger interface to the laser's SMA trigger input via the RF cable. This completes all wiring. The acquisition card has a built-in averaging algorithm. The data collected by the two channels of the acquisition card can be plotted as two real-time curves. The ratio of the two curves has an approximately linear relationship with the temperature. By calibrating the temperature of the test fiber optic cable, we can obtain the relationship between the temperature and the ratio. Realize the function of fiber optic cable temperature measurement. Of course, the reality also needs to take into account the length of the fiber optic cable, optical power, attenuation and other factors, and do the corresponding compensation algorithm. To realize the high-precision DTS temperature measurement system, it still needs technology. We have made all the equipment for the DTS system mentioned above into a hardware development kit, so please inquire if you are interested.